Swayam Prabha. Digital India. Educated India.
Welcome friends to this fifth and last lecture of week 7 of this NPTEL online certification course of environmental soil chemistry, and in this week we are talking about the redox chemistry of soils. And in the previous 4 lectures we have talked about some we have talked about the basic overview of redox reaction as well as what is redox potential. And we have also talked about the relationship of redox potential as well as pH. We have talked about the PE relationship. Remember, PE is basically the negative logarithm of electron concentration. Almost it is an intensity factor, just like the pH as well as redox potential. The PE sometimes used interchangeably with EH for denoting the submerged condition and as well as the oxidation reduction potential of the soils. Oxidation reactions are mainly useful for different chemistry applications. However, reduction reactions are basically used for different soil applications. We have talked about the stability relationship, stability line of different oxidized and reduced ion pairs, and we have talked about what is the cutoff line and which are the minerals which are more which tend more towards oxidation, and which are the ion pairs which basically shows their tendency towards getting reduced and or remaining in the reduced condition. Then we have talked about the classification of submerged soils. We have talked about the paddy soils, we have talked about subaquatic soils, marsh soils, and we have discussed their characteristics also. Side by side, we have also discussed about the implication of soil redox potential. Now, we started discussing about the characteristics of the submerged soils, and we have discussed some important points. Now, today we will going to start about discussing about this sequential reduction. Now, you know that the sequence of the reduction, as you can see in this slide, that the sequence of the reduction of various compounds in soil usually occurs in the order of oxygen, nitrogen, manganese, iron and sulfur. So, always oxygen reduced first, followed by nitrogen, then manganese, then iron, then sulfur, and basically it is concurrent, and this order is basically concurrent with decreasing PE levels. So, if you see the PE levels, obviously the PE will be highest in case of oxygen, followed by nitrogen and then manganese and then iron and sulfur and so on and so forth. Remember that at pH at PE value of greater than 7, oxygen is reduced to form the H2O, and with a decrease in the PE value, this is followed by reduction of nitrate to nitrite and so on. We will see that in the next slide. And also remember that reduction of MnO2 or manganese dioxide is reported to occur at the same PE level as that of nitrate reduction. We will also see that in the next slide. And then comes the reduction of FeOH and to ferrous Fe2 plus, and when sufficiently low PE levels have been attained, then we can see the reduction of sulfate ions and carbon dioxide. These are the last couple of ions or compounds which are which get reduced when there is a decreasing PE or redox potential. So, we will see that in the next slide. So, in the next slide, this is showing the sequential reduction. Obviously, you can see oxygen is first getting reduced to elemental hydrogen here, and basically it should be 2H2O. It is not it should be 2H2O. Now, then second, the nitrate get reduced to nitrite, which is very transient, but it is a reduced species nitrite. And also you can see that manganese dioxide getting reduced to manganese Mn2 plus, and followed by this FeOH whole 3 to ferrous. So, ferric hydroxide to ferrous, and then so on and so forth. You can see sulphate get reduced to sulphite, and also other compound like carbon dioxide, phosphoric acids are getting reduced to their reduced counterparts. So, basically all these reduction reactions are following the reduction in their corresponding redox potential. You can see here in case of oxygen, the redox potential is plus 830 millivolt. So, obviously that shows high tenacity of oxygen to get reduced to water. So, let us move ahead and see what are the major electrochemical changes we can see when the soil is submerged. So, there are couple of major electrochemical changes. First of all, you will see a decrease in redox potential. It is very common when you submerge a soil, when you saturate the soil with water. And secondly, you will see an increase in pH in acid soil. We have discussed this in the last class, in the last lecture, and also a decrease in pH of alkaline soil, when. So, basically you will see whatever their pH is, whether it is alkaline or acidic, the pH tends to converge to the neutral condition, that is a pH of 7. Then you will see the changes in specific conductance and ionic strength. Basically, after the submergence, you will see an increase in specific conductance, and then you will see drastic shift in mineral equilibria. Obviously, there will be drastic shift in mineral equilibria because of redox reactions, and then cation and anion exchange reactions will also influence by this electrochemical, by this by this submerged condition, and also you will see the sorption and desorption of ions will also vary depending on these chemical changes in the submerged soils. So, let us see in details what are the different types of conversion happens in case of different major elements which are present in the soil. So, let us first start with nitrogen system or nitrogen transformation in submerged soils. So, this picture basically shows some a good nitrogen dynamics in submerged rice soil. You can see here that this is the right route. So, obviously, this is the water surface, followed by this thin aerobic layer, and then followed by this anaerobic soil. So, one thing is clear that these ammonium ions, which you can see here, is getting is diffusing away to the plant root. So, basically in the aerobic zone, when we are applying different urea or ammonium fertilizers, these ammonium get converted to nitrate through the process of nitrification, since it is an aerobic layer, and also the nitrate get fixed by different atmospheric fixation. So, and these ammonia also get lost due to the formation of ammonia through volatilization process, as you can see here. So, when you apply the urea ammonium fertilizer, it is get either nitrified to nitrate or either get volatilized to ammonium. Then this nitrate goes downward, showing a diffusion through a diffusion process, and this nitrate either leached away from the soil, or it is getting denitrified through denitrifying bacteria to produce the reduced form of nitrogen, that is either nitrous oxide or elemental nitrogen, and these elemental nitrogen and nitrous oxides release into the atmosphere. Also, these nitrogen from the atmosphere get fixed through the biological nitrogen fixation, and also due to the addition of organic manures and crop residues, the organic nitrogen will form. So, biological nitrogen fixation will produce the organic nitrogen, and also manures, addition of manures and crop residues also produce organic nitrogen. These organic nitrogen through the process of mineralization produce the ammonium. This ammonium get fixed into the 2:1 type of clay mineral, or they can further be immobilized into the inorganic forms. So, these ammonium get either fixed or immobilized in the organic form. Now, these ammonium can diffuse away to the root zone of the rice plant, so that they can take up this ammonium as a source of nitrogen. Also, these ammonium shows upward diffusion into the aerobic layer, and this aerobic layer further in the aerobic layer it further undergoes the nitrification. So, this picture basically shows a very good illustration of the nitrogen dynamics in case of submerged soils. So, mineralization of nitrogen is basically restricted to ammonification stage. Obviously, it cannot in the anaerobic layer, the mineralization of nitrogen stopped into this ammonium formation. It cannot go beyond that because there is no oxygen, and also ammonification of organic matter also proceed to a very lower rate. Because of devoid of this is the surrounding is, or the environment is devoid of oxygen, and also intermediate products of decomposition forms in this anaerobic layer. So, this is basically in short the nitrogen dynamics in the submerged soil. So, let us consider phosphorus dynamics in submerged soil. The mobility of phosphorus is higher in submerged soil because of diffusion process get increased, and then the phosphorus mobility or phosphorus mobility is restricted to the top 30 centimeter layer of the soil even in submerged condition. Remember that the phosphorus fixation is more in the form of chemisorption on the colloids. So, the fixation is more, but at the same time when there is a fixation, the colloid fractions of phosphorus also get mineralized, releasing or increasing its availability. Obviously, when the colloid fractions of phosphorus get mineralized, it results in more availability because it converts into the more available and more soluble forms. And also remember that the solubility of phosphorus compounds get increased due to the presence of carbon dioxide and decrease in EH. So, hydrolysis of phosphorus compounds and its solubility will be more, leading to higher solution of phosphorus. So, as a result of that, and also the mineralization organic P will be higher. So, as a result of all these processes, the phosphorus availability in submerged soil is relatively higher than that of oxic soil or in case of aerobic soil. So, in case of submerged soil, the phosphorus availability generally increases. Now, let us talk about the potassium in submerged soils. Now, it increases, generally the potassium availability increases due to the presence of a ferrous ion, which, and also this potassium get released from micas in the submerged soils. So, their availability increases. Sometime the availability of applied potassium decreases due to the formation of some sparingly soluble iron potassium complexes. So, mostly the potassium availability in the submerged soil increases. However, in some cases where there is a formation of sparingly soluble iron potassium complexes, then the applied availability of applied potassium decreases. Now, if we talk about the sulfur in the submerged soils, the sulphate, which is an oxidized form of sulfur, reduced to its reduced form, that is hydrogen sulfide, and then in the extreme condition it reduced to iron sulfide. So, it has basically, when it reduced from sulphate to H2S and then to FeS, it has basically three implications. First of all, sulfur supply may become insufficient, okay, because in case of plants the available form of sulfur is sulphate. However, the sulphate is getting reduced to the sulphide form. Then zinc and copper may be immobilized in the form of zinc sulphide or copper sulphide, and then the H2S toxicity or hydrogen sulphide toxicity may arise in soil which is low in iron. So, when this soil is low in iron, the iron sulphide will not form, the hydrogen sulphide will form, and as a result of hydrogen sulphide you will see the sulphur toxicity, as you can see in this roots of the rice plants. So, this is because of the hydrogen sulphide toxicity. Okay. So, let us talk about the manganese in submerged soils. Now, in case of aerobic condition, the manganese dioxide is present, and when it is getting reduced in the submerged condition due to the reduction of redox potential, it converts to the Mn2 plus form and then also water. Now, this Mn2 plus is water soluble and available to the plant, and the above this reaction is basically occurs almost coincident with the disappearance of molecular oxygen and nitrate nitrogen, resulting in formation of manganese compounds. So, when the oxygen get depleted due to the submerged condition and nitrate nitrogen getting utilized by the microbes which are present into the anaerobic condition or facultative anaerobes, then what happens, this manganese oxide MnO2 or these manganese dioxide basically convert to manganese compounds, that is Mn2 plus. Now, water soluble and exchangeable ion increases on submergence and ensures a better supply of manganese in a flooded soil to rice. So, in case of flooded condition, the availability of manganese increases. Now, to talk about the iron in submerged soils. Now, in the iron in submerged soil, basically in waterlogged condition, ferric is reduced to ferrous. We have already discussed that, with concomitant increase in iron solubility by anaerobic bacteria, which uses iron oxides as electron acceptor in respiratory chain or terminal electron acceptor in the respiratory chain. So, basically the iron or ferric 3 reduced to Fe2 plus by anaerobic bacteria, and it produces toxic effects. When the iron get increased, the toxic effect of plant can be seen, which we call bronzing or bronzing disease. As you can see in this picture, it is showing the bronzing of the rice plants. Now, under anaerobic condition, owing to the reducing process, hydrous iron oxide give rise to Fe2 plus according to the following equation. As you can see, FeOH whole through, when it is getting reduced by accepting 3 protons and electrons, it is reduced to Fe2 plus and producing 3 molecule of water. So, this is how the iron get reduced into the submerged condition and producing the iron toxicity. Now, let us talk about the zinc in submerged soil. Now, zinc deficiency in flooded soil thought to be related to high pH or the presence of calcium carbonate. However, zinc deficiency also occurs in acid soils. Now, when the soil is submerged, the concentration of many nutrients increases, but not zinc. So, you can see when we are submerging the soil, the concentration of phosphorus, available phosphorus increases, available iron increases, available manganese increases. However, in case of zinc, it is not, we cannot see this thing. Now, in acid soil, zinc deficiency may be attributed to the increase in pH under reducing condition and subsequent precipitation of franklinite or sphalerite. Now, decreasing the pH in submerged calcareous would usually increase zinc solubility. However, higher the soil pH, poorer the aeration and greater the zinc deficiency. So, you can see both in highly alkaline soil as well as in acid soil, zinc deficiency occurs as a result of submergence. Now, the next thing we are going to talk about is the redox reactions involving different inorganic and organic pollutants. Now, you see that manganese with the oxidation number of 3 and 4, then ferric, then cobalt with oxidation number of 3, then lead 4, all these oxides and hydroxides are thermodynamically stable in oxygenated system at neutral pH. So, in case of aerobic condition, they are thermodynamically stable. However, under anoxic condition or submerged condition, when we submerge the soil with water, reductive dissolution, a new process called reductive dissolution of these oxides and hydroxides occur, and this reductive dissolution of these hydroxides and oxides occur through some agents, and these agents are either could be inorganic or it could be organic. Now, here I have shown here two examples. Here you can see the reduction of MnOH and MnO2 and how it happens. So, you can see here this Mn3OH, which is a solid, when it is getting reduced, it produces the Mn2 plus. Okay. And when this Mn4O2, basically MnO2 get reduced, it is produced the Mn2 plus. Now, you can see in both these conditions the oxidation number get reduced, that means they are getting reduced. So, changes in the oxidation state of the metal associated with the oxides above can greatly affect their solubility and mobility in soil and in the aqueous environment. How? We will see, and how this happens we will see. Now, these reductants can either be, as I have told you, the reductants can be either inorganic or organic in nature. Okay. Now, there are a number of natural and xenobiotics organic functional groups. The xenobiotics means synthetic organic groups. So, natural or synthetic organic groups that are also good reducers of oxides and hydroxides, and basically they include either carboxyl group, then carbonyl group, phenolic group and alcoholic functional group of soil organic matter. So, you can see there are two types of reductant, one is organic reductants, another is inorganic reductants. For example, in case of organic reductants, you can see the microorganisms in the soils and sediments are one example of organic reductants. However, as far as the inorganic reductants are concerned, you will see arsenide, then chromium with 3 plus and then plutonium 3 plus. Now, let us see different redox reaction involving pollutants. So, in this table you can see the reduction half reaction along with the these reduction potential and also more realistic reduction potential, environmental condition reduction potential at pH 7. So, you can see it shows the reduction of Mn4 to Mn2 plus, Mn3 to Mn2 plus, Fe3 to Fe2 plus, Fe3 to Fe2 plus. So, basically one is goethite, another is hematite, and then magnetite again Fe3 to Fe2 plus, and cobalt 3 to cobalt 2 plus. So, we can see all these cases they are getting reduced. Okay. So, now let us extract some other information from this table. So, what are these? So, one thing is clear that oxidant strength decreases in the order of Mn4, 3, Mn3 or 4. So, you can see Mn3, Mn4, okay, and which is greater than this cobalt 3 oxides, which is further greater than Fe3 oxides. Okay. Fe3 oxides, you can see these are the Fe3 oxides. Okay. And this is basically the oxidant strength we can see based on this standard redox potential. So, you can see in case of Mn4 in both this condition it is positive followed by this cobalt, and then in case of iron it is already negative. So, obviously, among all these fractions the manganese Mn4 and Mn3 will show the highest tenacity to get reduced, followed by this cobalt and then followed by this Fe3 ions. Now, these iron oxides are more difficult to reduce than Mn3 and Mn4 species. Obviously, since these Mn3 and Mn4 are having positives, so they are always easy to get reduced. However, in case of these iron oxides, they are already having negative redox potential. So, their tenacity to get reduced is always low. Thus, Fe2 plus is easier to oxidize than Mn2 plus. Obviously, the species which is less tend to get reduced obviously will be tending towards getting oxidized, because of obviously as you can see they have negative redox potential. Now, another information we can see that the goethite and hematite could only oxidize oxalate, and they are not strong enough oxidants to oxidize hydrogen sulfide, ascorbate or hydroquinone. So, since you can see they are already having the negative redox potential. So, they are always tends towards their tenacity to get reduced is very low. So, obviously, they can oxidize only oxalate. So, oxalate, so they are not strong. So, they are not strong enough oxidants to oxidize the hydrogen sulfide, ascorbate and as well as the hydroquinone. However, at pH 4 the Fe3 plus oxide can oxidize all the reductants. So, these information we can gather from this table. And also you can see reduction half reaction along with the several organic compounds like hydroquinone, ascorbates, hydrogens so ascorbate, hydrogen sulfide, oxalates. So, as we have told that goethite and hematite could only oxidize oxalate. So, oxalate have, let us see what is the redox potential of oxalate. It is minus 69, which is less than this hematite and goethite. So, obviously, it can further oxidize these oxalates, but not the hydrogen sulfide, ascorbate and hydroquinone. So, what is the mechanism for reductive dissolution of metal oxides and hydroxides? Now, the reductive dissolution of metal oxides and hydroxides occur in three following steps. First step is diffusion of the reductant molecule to the oxide surface. Second step is surface chemical reaction. After it reach to the oxide surface, it produces some reaction in the surface, and then third is release of reaction products and diffusion away from the oxide surface. So, you can see there are three processes. Now, among these three processes, the first one and third one is transport steps. Obviously, one is getting at towards the reductant molecule going towards the oxide surface, and then reaction products are diffusing away from the oxide surface. However, the rate limiting step is the reductive dissolution of oxides appear to be surface chemical reaction of the second step. So, this is the rate limiting step. Now, let us see how it happens. Now, this reductive dissolution can be described by both inner sphere and outer sphere complex. We have already seen what is inner sphere complex and outer sphere complex in our previous lectures. Okay. Now, this inner sphere complex and outer sphere complex based reductive dissolution can be expressed in terms of three mechanism. One is called precursor complex formation, second is electron transfer, and third one is called the breakdown of successor complex. Let us see in details. So, here the reductive dissolution can be described both in terms of inner and outer sphere complex, we have already discussed. Now, inner and outer sphere precursor complex formation, that is the first step or first mechanism. Precursor complex formations are adsorption reactions that increase the density of the reductant molecules at the oxide surface, which promotes the electron transfer. So, obviously, we know that the first step is the transport process, and when the reductant get attached to the oxide surface, where it produces the precursor complex form, it forms the precursor complex and then promotes the electron transfer. In the inner sphere mechanism, the reductant enters into the inner coordination number sphere via ligand exchange and bonds directly to the metal center prior to the electron transfer. So, you can see this shows these three mechanism in detail. So, first of all is the precursor complex formation. You can see both in case of inner sphere complex and outer sphere complex. In the inner sphere complex, there is M3H2O whole 6 3 plus. You can see it is one example is given by phenol. So, you can see the inner sphere complex is produced and then it is reduced. So, this is a precursor complex, and also in case of outer sphere complex, it is a precursor complex, and then the second step, electron transfer is happening. Electron transfer, you can see between it is electron transfer is going on between these A and these. So, when the electron transfer happens between these metal as well as these uh, of this group A group of phenol, then we can see that it reduced to Mn2 plus. Similarly, here you can see, and in the third phase obviously the breakdown of the successor complex. So, you can see the successor complex further break down to release these A, and then ultimately reducing the complex to M2. So, basically in the 3 steps in both inner sphere and outer sphere complex, you can see the precursor complex formation. This is the first step. Second is electron transfer, you can see here from metal to the A group of the phenol, and then breakdown of successor complex, where it is further breaking down to produce the successor complex with a reduced compound, which is having the oxidation number of 2 in case of metal. So, this is how the reductive dissolution basically occurs. Oxidation of inorganic pollutants, manganese oxide can oxide a number of environmental important ions like chromium and plutonium. You can see here this plutonium, also chromium, it is getting chromium 3 is quite stable, and also it is get oxidized to chromium 6, which is very toxic and it is a carcinogenic, it is very carcinogenic, and this oxidation is mediated through manganese, and also you can see the conversion of chromium 3 to chromium 6 happens by most of these reaction, basically oxidation occurs in the first hour. At higher temperature there is a rapid oxidation rate followed by slower rate, and the decrease in the rate of chromium 3 oxidation has been ascribed to a number of factors, including the formation of surface precipitate that effectively inhibits further oxidation, and also you can see that these manganese can oxidize the plutonium. Here you can see that if we plot the time and oxidized chromium formation, obviously as the temperature increases, higher temperature, the rate also rapid oxidation, we can see the rapid oxidation. Okay. So, these are different types of oxidation mediated by inorganic manganese. Also similar in case of arsenic, arsenite can be oxidized to arsenate, which is As5. So, this arsenite can be converted to arsenate by a set of reactions, and these reactions have been defined here, and ultimately producing from arsenic with a 3 oxidation number to arsenic with a 5 oxidation number. And this reaction involves the formation of an adsorbed layer. Oxygen transfer occurs in the here there is an adsorbed layer, and you can see the oxygen transfer occurs, and HASO2, which you can see HASO2 is oxidized to H3ASO4, and ultimately these arsenite converted to arsenate. So, these reactions are inorganic redox reactions with manganese dioxides are given here. You can see ultimately summarily we can see arsenic 3 can be oxidized to arsenic 5, selenium 4 can be oxidized to selenium 6, then chromium 3 can be converted to chromium 6. And these are the time to oxidize to 50%, and this is the driving force which is basically oxidizing this species. Now, this is the last slide. Obviously, it is basically you can see that the reductive dissolution can not only occur through these oxidation not only occur through manganese oxide, which is an inorganic mineral, and also in the reductive dissolution also manganese oxides can be mediated by different organic pollutants also. We have seen that the reductive dissolution, because phenol is attaching, remember the phenol is attaching and then it is reducing the Mn4 to Mn2. So, with substituted phenols the rate of dissolution was proportional to substituted phenol concentration, and the rate basically increase at pH decrease as pH decrease, and phenol contain different alkyl, alkoxy and other electron donating substituents which are slowly degraded, and para-nitrophenol reacted slowly with Mn3 and Mn4 oxides, and the increased rate of reductive dissolution at lower pH may be due to more protonation that enhance the creation of precursor complexes or increase the protonation of protonation level of the surface precursor complexes that increases the electron transfer rates. So, guys, we have come to the last slide of our week 7. So, we have discussed in details about the different chemical dynamics of submerged soils, and we have discussed in details about the redox chemistry of soils. Although there are some other points which still need to be covered. However, if you are interested, you should consult these books like Environmental Soil Chemistry by D. L. Sparks. You can also consult the Nature and Properties of Soil by Niles C. Brady and Will, and also you can consult this paper, which is one of the seminal paper, Chemistry of Submerged Soil by Ponnam Peruma. And so, these will give you more enriched information about the nutrient and other elemental dynamics under the submerged condition. So, let us wrap up this week and this module. Let us meet in our next week or next week of lectures, and then we will start a new module. Thank you very much.